Hey, everybody. All right. Awesome. 26 of us, I think we are all here. So, let me go over what we're going to do when you guys come back on Monday. Of course, some of you will be back and some I'll still be, recording the Zoom meeting that we have. So in alphabetical order, let me bring up real quick my, let me bring up my class list and take a look at you guys. Those of you from 1, 2, 11, 12. All right. So those of you from Ball. Sorry about that, Jasmine. Those of you from Ball to Jordan Johnson, you guys will come at noon. And then from Megan Kite all the way down, who's my last person? Savannah Varner, though that group, you guys will come at 1. And we will be meeting in, let's see, we'll be meeting in the lab in 105. If for some reason you can't make it to the noon session, but you can make it to the 1 o'clock session, just send me an email and let me know so that everybody gets their time in lab. And we'll split it up most weeks like that until we can get everybody vaccinated. I'm running a little bit behind today because that's what I was doing, is getting my first shot. So.
Is this for Wednesday? Because we don't have class Monday.
Oh, yes, it is. Thank you, Jordan. Okay. I totally forgot that we get that day off. All right. So yes, that'll start on Wednesday. All right. I am going to share my screen.
I'm assuming I'm in group 1. My last name starts with an A. I just want to make sure that that's where you want me to go.
Yes, I wonder why. Where are you? Oh my gosh. Yes, you are in group 1, which means that we stop. For some reason, I wasn't scrolled all the way up, which means we stop at Hannah Hostetler. So Jordan, you'll be in the 1 o'clock session. Okay?
Okay.
All right. So let me go ahead and get us started. This is a much better lab, or this is a much better day to actually have lab. So sorry, this is what you get. All right, can everybody see my screen? Yes?
Yeah.
Okay.
Yes.
All right. Then let me go ahead and present. Come on. There we go. So we're looking at something which sounds really easy today. Do things sink or do they float? And so I just want to start off, usually we're in lab when we do this and we actually make predictions and you watch things, but today I did the best we can. So you're going to make some predictions, and I'm recording this so you can go back and write these things down when you work on the lab. I did just come over from the bookstore as well, and they still don't have our manual printed, but this isn't good news, but at least I know it's not just us. They don't have manuals printed for a lot of biology or math classes either. So there's something that's going on with the online portion of the bookstore and then our physical bookstore. There's some kind of disconnect. So as long as we're waiting on manuals, I'll keep making PDFs for you guys. All right. So without any further ado, all I want you to do is predict whether the items that I show you in the list are going to sink or float. And then I'm going to ask you why. All right, so here we go. So here's my list. A regular orange, and then if I peeled the orange, a can of Diet Coke and a can of regular Coke, a flat piece of aluminum foil, but a piece, and then a piece of aluminum foil that I roll up in a ball. First off, are there any chemical changes that I am making to any of these items? Dawson, I'm gonna pick on you since you didn't show up last time. Am I making any chemical changes to these, or are they physical changes?
Physical.
All right, so they're just physical. I'm going to peel the skin off of an orange. All I'm going to do is have 2 different cans of Coke. That's no change at all. And then I have a flat piece of aluminum foil, then a piece that we balled up. So I want you to make your predictions right now. Like, jot it down on a sheet of paper. Rachel, what do you think about the orange?
I think the orange would float.
Okay. And trying to remember names. All right, Megan, what about an orange that I peel?
I think it would do the same.
Okay. And Abigail, what about a can of regular Coke?
The can has Coke inside of it, right? It's not an empty can.
No, correct. It's a full can of regular Coke.
I think it's going to float.
Okay. And Hannah, what about a can of Diet Coke? Same size, same, it's still full, sink or float?
I think it would float.
All right. And I'm trying to think of names off the top of my head. Is it Aaliyah? What about the flat piece of aluminum foil?
I think it would float.
Okay. And I can't see names right now because I'm in a shared screen. Aaliyah, pick somebody else for me.
Grace.
All right, Grace, what about a piece of aluminum foil that I just wadded up in a ball?
I think it'll sink.
All right, so let's take a look at these things. Ta-da! The orange with the peel floats. The orange without the peel, even though it now has less mass, it sinks. So that's a strange one, because a lot of times, little kids, big kids, adults, you know, we think about, okay, if it's heavier, it's going to sink. I'm going to shut up right there. Regular Coke sinks. Diet Coke floats. They are the same size, same volume. I want you to think about why that might be different. And there is our aluminum foil, which most of you got right. And we have the flat piece, of course, floats. But once you wad that piece up into a ball, it sinks. So We're going to take a look at some things and decide why in the world these things happen. First of all, we're going to need to review some terms. And let's see, again, I can't see names right now. So Grace, could you pick the next person to answer?
Abigail.
All right, Abigail, what is matter?
Matter, isn't that what we talked about last time with atoms matter consists of atoms?
It does, and matter is anything that has two qualities.
Compounds.
If you want to pass it to somebody, you're welcome to.
Compounds?
No,
I don't know, maybe I'll pass. I thought matter was like everything that's around us.
it is, but there's a
Mass?
definition. It takes up space and has mass. So it has volume and mass. Anything that takes up space and anything that has mass. That's what matter is. Matter also has different properties, and different matter have different properties. But one of those things is density. And density is a little bit different from mass. You know, mass, when you combine mass with gravity, that gives you your weight. Your mass is not the same as your weight. Density is not the same as weight. Matter also has forces that are exerted upon it. And a force, of course, a force is a push or a pull on an object, like gravity is a force. So let's talk more specifically about density in relation to why things float. So the definition of density is right here. It's like the mass per unit volume, or basically it's how much stuff is packed into a set amount of space. So if you tried to fit 50 milliliters of water in a 20 milliliter beaker, that's not going to fit. But the density of the water doesn't change. The density is still the same, because density also doesn't rely on the amount of the object you have. For example, the density of one drop of water is the same as the density of any other fresh water that you can think of. Like, it's the same as the density of the water in the Ohio River. It doesn't matter how much you have, density is the same. Same with a piece of iron. If you just have a little tiny nail, that density in that little nail is the same as if you had a railroad spike, if it's still made of iron. So different matters have very set densities. Math. Oh, here we go, guys. You get some math again. This is an equation that you're going to need to know. Your density is equal to mass times volume. You might want to jot that down right now, because we're going to do a little math later on. The density equals mass times volume.
Is it times or divided?
I'm sorry, it's divided by, I'm looking at it and saying the wrong thing. I apologize. It's mass divided by volume. It is grams per milliliter or grams per centimeter cubed. And yes, it is division. And so that is how you get anything's density. And I want you to jot this down as well. This is important. 1 milliliter. So if we're measuring the mass of a liquid, it is actually the same volume as 1 cubic centimeter. You know, when you get a shot, they usually call them cc's. That's a cubic centimeter, or the cm cubed that you're seeing there. All right. But we'll come back to that. So calculating density. First of all, we use a balance down in the lab, the electronic balances. If you were in Exosphere last semester, you know, we use the quad beam balance. That was, you don't normally use those in the classroom. We use our electronic balance to get our mass, and we make sure that it measures in grams. Our volume, for liquids, we use graduated cylinders. And that's like the tall glass thing that we use to measure amounts of water in. And they have the numbers on the side. That's a graduated cylinder. For regularly shaped objects like blocks, it's length times width times height. But what if I gave you a rock? You know, a rock isn't going to be a regular shape. I wonder how we would measure the volume that way. Well, since a cubic centimeter is the same as a milliliter, we could look at how much water gets displaced. Rachel, call on somebody, please, because I know I've already used you.
Let me see names. Megan.
All right, Megan. So if you all right, let's pretend that you have run a tub full of bath water.
Okay.
You sit down in it. What happens to the water level?
It's gonna rise.
Okay. So what we could do to measure Megan's mass is measure how much water comes up in the bathtub. This is the same way you'd measure a rock. Fill up your graduated cylinder, say, let's just pretend to the 50 milliliter mark. You drop your rock down inside. However far up the water level rose, that is the volume of that rock. So if it raises 3 centimeters, or I'm sorry, 3 milliliters, that means that the volume is the same as 3 centimeters squared. Like I said, it's really important to remember that milliliters are equal to cubic centimeters. In your lab that you guys are going to have for homework, you're going to have to refer back to this slide. And I may help you. Actually, let me have you practice right now. That way we will have at least done this. We are going to practice getting the density of, let's do ice. And the density of ice is 0.92 grams per cubic centimeter. All right. And I'm also going to do lead. Actually, you guys are going to do lead. And the density of lead is 11.3 grams per cubic centimeter. So I'm going to stop sharing that. We're going to put up a whiteboard, but I'm going to have all of us have permission to write on the whiteboard. All right. It's a little bit harder when you don't have a touch screen. Yeah, mine's not. All right. Did everybody see the whiteboard?
Yes.
Yes.
All right. So I'm going to put we have density is equal to mass divided by volume. Okay. So let's say that we have, let's see. So ice. We know that the density of ice is 0.92. And Erica, are you in this class?
Yes, I'm in here.
That's what I thought. And what are the units for density?
Just would it be 1 centimeter cubed?
You're getting there. It's grams per.
Grams per centimeters cubed.
Yeah.
Okay.
So those are the units for density. So Erica, call on somebody to do this math for me.
Sarah.
Right, Sarah, I'm going to pretend that we have an ice cube that is 100 centimeters cubed. I want you to tell me what the mass of that ice cube is. And you can draw on this board as well. I'm going to give you a different color from me. So you get dark blue. So
Would I just multiply 0.92 times 100?
yeah, can you work on the whiteboard for us?
Sure. It's not letting me draw.
Okay, you can tell me the answer and I will do it for you.
Okay, I got 92 grams.
All right. And she's right. Because all we do is multiply both sides by 100. That cancels that out. And when I multiply by 100 centimeters cubed, it cancels out, it cancels out our little units there, and we're left with grams. Good job. You're going to have the same problem. I think it's using lead in your lab. Is there anybody who needs to do one more practice?
I do, if you don't care.
No, I don't care. Is that Abigail?
Yeah, you know it.
All right. So, Abigail, I'm going to have you walk me through this. What did we say the density of lead was?
11.3
All right.
centimeter cube.
All right. And I'm going to say that the mass of our lead is, I won't make it too hard. Let's say that we only have 10 grams. It's not very much lead. We have 10 grams of lead. How much volume does 10 grams of lead take up? What am I going to do first, Abigail?
Are we just doing the same thing, like how you multiplied on the first problem?
But I want my volume on top and by itself.
Okay, I don't know what to do then. Sorry.
Okay. Well, the first thing I would do is I'm going to multiply both sides by V so that I can have it on top of the fraction bar. Okay.
Okay.
And now I've got 11.3 times V equals 10. How do I get rid of the 11.3?
Multiply?
Well, since the 11.3,
Or we're gonna divide.
yeah, right, since the 11.3 is a whole number, we have to divide both sides by 11.3.
So if we're finding the volume, we divide, and if we're finding the mass, we multiply.
Correct.
Okay.
All right. Do you have a calculator with you?
I don't, but I have my phone.
Okay. So what do you get for an answer?
Okay, sorry, I got 0.88. Did I do that right?
Yep. And what are my units for volume?
Just wait. Volume. Hold on, bud. I'm doing homework. You got to go back in there. Okay, so that's what I thought it was. Centimeters cubed.
Right. So do you see how tiny that piece of lead is?
Okay, yeah.
All right, it's not going to take up very much space because it has such a high density. And so a smaller piece is going to take up very little space. So it's going to take, more practice for us to, be comfortable with what all of that means. But that's a start for us. That's a start. All right. So we're going to talk about something that is very related, but a little bit different from density. And that is buoyancy. And buoyancy is a force. Forces are measured in newtons. Like of course I'm talking about in the metric system. So buoyancy is measured in newtons. Your weight is measured in newtons. So it's a force that pushes an object upward, and it makes it seem like it loses weight in fluids. And that a fluid is considered air or liquids. And before I talk about Archimedes' principle, let's say that we have a balloon. Let's see, Abigail, call on somebody that you haven't heard from yet.
Is it Aaliyah? I don't think we've heard from her. I don't think.
All right. Aaliyah, let's say that you blow up a balloon just with your mouth. Is that balloon going to sink or float in the air?
Sink.
Right, because because it's more dense. The air coming out of your lungs is more dense than the air around us. Aaliyah, call on somebody else for the second part of this problem.
Alexis.
All right, Alexis, now I'm going to give you a helium tank. Now we know that balloon, if we just had a plain old balloon, it's going to, if I drop it, it'll drop to the floor. What if we fill it up with helium? What's going to happen?
It's going to float.
Why?
Because you're using helium and it's not from you.
Okay.
I don't know.
No, that's okay. I want you to think about helium. Is it less dense or more dense than the air around it if it floats?
Less.
All right. And so helium can cause that balloon to have buoyancy. Let's take a look at Archimedes' principle. A buoyant force is equal to the weight of the fluid that the object displaces. So let's go back to the bathtub problem. When we talked about you are sitting down in the bathtub. Now, everybody in here is going to hit the bottom of the bathtub. But now let's put everybody in a swimming pool. The buoyant force is equal, like the force pushing up on you is equal to the weight of the water your body is displacing. I'm going to use Abigail as an example. She's a tiny little thing. The buoyant force that pushes up on her is going to be equal to her weight. So she's pushing down on the water, and then buoyancy is keeping her floating, but it's equal to her weight. Now me, I'm going to get in the pool beside of her. I'm going to sink further. And the buoyant force that's acting on me is going to be stronger to keep me floating than it would be on Abigail. That's what Archimedes' principle is kind of driving at. So if you're having trouble understanding that just by reading it, which that's completely understandable, I want you to think about getting into a swimming pool. What causes you to float? That force is equal to your weight. And so, buoyant force, if buoyant force is stronger than the weight of an object, then it floats. If the buoyant force is less than the weight of the object, it's going to sink. What happens if the forces are equal? Don't everybody answer at once. You just have something called neutral buoyancy. That's all. So let's keep going here. So the whole thing that we're talking about today is like why things float. When you guys are elementary teachers, this is truly, it's one of the things that you guys will deal with in science class and even in some of your math classes is density, not in K through 2. But you know, those kids are not ready to think about that kind of math. They're not ready to think about even that sort of a two-dimensional relationship. So things float because they are less dense than the fluid or the air. All right, so the liquid or the air in which they're immersed. So it all has to do with density and buoyancy. The buoyant force is greater than the weight of the object. That'll also make it float. I want to go back to the whole orange problem. Erica, would you call on somebody for me?
Trying to look through the list. Aislinn, is that how you say it? Sorry if I messed it up.
No, that's how you say it.
Okay.
All right, Aislinn. So you can explain it to me using density or buoyancy. I'm probably going to ask for both. Explain to me why the orange that had the peel on it floated.
Because it's less dense than the water.
What made it less dense?
The peel?
Okay, keep explaining. You are on the right track.
The peel, I'm not sure.
You are so close. So you've got that peel that almost acts like a life jacket. And so the buoyancy of the water pushes up on the orange and causes it to float. So the buoyant force is greater. But if we look at density, does the peel weigh very much compared to the rest of the orange?
No.
No, it doesn't. The rest of the orange has the most mass, but the peel on a lot of oranges is pretty thick. And so if we go back to that whole density equals mass divided by volume, when you leave the peel on the orange, it doesn't really increase the mass very much at all, because it's not, it doesn't weigh that much. But it increases the volume. So it spreads it out. It's kind of like that aluminum. If you wad it up in a ball, you create less volume. So the density increases, which makes it sink. Same thing with the orange. When you increase the volume, you spread things out. And so the density decreases when things are bigger, spread out. Compare it to this. If you jump off of a high dive, Dawson, if you jump off of a high dive and you completely spread your arms and legs out and you go face first into the water, what kind of force are you going to hit that water with? Is that going to feel good?
You're not going to go too far down.
Exactly, because you have spread everything out. You have decreased your density because you've increased the volume or the space you're taking up. But if you jump off the high dive, you haven't gained or lost any mass. You jump off that high dive and you pull your legs together and you point your toes and you pull your arms into the side. Rachel, then what's going to happen to you?
Yes.
What's going to happen if you jump off the high dive and you're just straight as a board?
You'll probably go as close to the bottom as you can.
Exactly, because we've decreased your volume. Your mass is the same, but if we decrease the volume, you raise the density, which means you are going to sink further. So these are the ideas that I want to get across to you guys. So the other day, we also talked about when the earth formed, we talked about something called differentiation. Aislinn, what was differentiation?
That like all heavy things sink to the middle and the lighter things are on the outer edge.
Exactly. And once that happens, once we have differentiation, we also began having things like plate tectonics, which we will go over in great detail during this class. But you have things like mountain building because of that in the earth. And as mountains erode, their mass decreases. Well, when it decreases, the underneath of a mountain gets pushed up. And so the mountain itself stays in equilibrium. That is called isostasy. And it's kind of this equilibrium between the crust and the upper mantle. So as things lose mass, the mantle pushes up. And we'll get back to that later on this semester. But that is something that's very similar to what's happening. That floating and sinking happens on a global scale as well. It's also called isostatic rebound. That'll be something later. And so if you look about, or you think about the layers of the earth, you've got this crust and you've got continental crust. Well, the continental crust is less dense than oceanic crust. And because it's less dense, it is higher than oceanic crust. just think about it. The longest mountain chain in the world is under the Atlantic Ocean, but the highest mountains on the surface of the Earth, they're not underwater. They're at the surface. That's because continental crust is less dense, so it rides higher than oceanic crust. All right, so if we were in lab, this is what we would be doing. Because we can't be in lab, this is not this is not what you're going to do. Let me see. Sorry. Let me stop that real quick and show you what you are going to be doing. Oh, whoops, we're not in day one. That would help. All right, let me share this with you. All right, so this is going to be your homework based on, and I did record this this Zoom meeting, so I will again post this in your supplemental material, your support material. So your think or swim homework. I'm gonna have you guys go to the West Virginia tree website, and you're going to look at what grade level do they teach buoyancy in, and just tell me what the CSOs are. You can just list them. You don't have to write the whole thing out. And then I want you to explain to me, why don't they teach density in like K through 2? You know, pretty simple stuff that we're talking about here. For the application questions. All right, so this, I know it refers to the lab. Everyone used different size rocks. Explain how it does or does not matter when calculating density. Well, that was part of what we talked about. Remember that density does not matter about, you know, it doesn't matter how big or small the sample is. The density is going to be the same. And is there anything else? No, there are just 10 questions I have. And number 9, if everybody will look at number 9, it says that you have a chunk of iron and it's 30 centimeters by 10 centimeters by 2 centimeters. So you're going to have to calculate the volume first, and then you're going to have to find the mass. All right? So it's a little bit more than what we talked about, but that'll be your homework. And I know that we're finishing up early today. That's because we don't get to have lab. Do you guys have questions? I know that's a lot to go through. And that's why I record this in case you need to go back.
I have a question.
Yes.
When dealing with length times width times height, will it ever matter like which one you use as length or which one you use as width? Does that make sense?
Yeah, and as far as this class is concerned, no, because as long as they're all 3 in the same unit, like these are all 3 in centimeters, it doesn't matter.
Okay, thank you.
Anybody else?
I had a question about the earthquake homework.
Yes.
Are we supposed to like print out the map and draw the earthquakes on there? Like label them on the map?
Yeah, you're just going to like put little dots where they occurred.
Okay, and then for the table, do we need to like include the day of the week that it happened?
No, because we're just doing a 7-day table, it's just going to be a tally. And guys, I know that I have the wrong due date on there. I'll go in and fix that. Because, you know, it's not going to be due until next Wednesday.
So you don't want a table per day. You want one table with all the 7 days included.
Correct. And the only thing you're going to do is separate it into category 2, category 3, you know, on up through 9.
So
Like-
we should start today since it's 7 days.
Yes. But remember the website, you could do all the way until, you can wait until Tuesday, and you can click on worldwide earthquakes past 7 days. And then you can just use that data that day.
Okay, and what day is the Think or Swim due?
This one shouldn't be due. Oh, let me see real quick. This one is due next Wednesday, January the 20th.
When we're plotting the earthquakes on the map, do you want a different map for each day or just put them all on the same map?
Put them all on the same map.
Okay, so everything is just all on the same thing over the 7 days.
Yes.
Okay, that
The
makes
map is going to be a mess.
sense.
Any other questions?
Do you want us to you want us to differentiate the color by like 2 point whatever is one color and 3 point whatever is another color, but do you want us to say what days they
No,
are?
You
Okay.
have to tell me which days, but I do want, yeah, you know, your 2s will be whatever color you pick.
Okay. Thank you.
Anybody else? Oh, I didn't hear from Cecily today, or Jasmine, or Bernice, or Molly. Well, trust me, I'll pick on you before this is all said and done, just not today. Delaney or Sabrina. All right. Anybody else have questions before I let you go and get out?
Really quick, last class you wanted us to start it yesterday, but now you said today. So should we get rid of, if we started it, should we get rid of that data?
No, if you've already started it, that's fine. That's why I said 7 days. Some people like to start it the day that I assign it. Other people like to wait a couple of days and then start it.
Okay.
As long as you have it for 7 days by next Wednesday, you're good. All right. Well, once again, like I said, I will, I take this recording and I upload it to YouTube and then send you guys the link. And I think that's all I have for you guys. So it was nice to see everybody. Well, I didn't even see half of you, but it's always good. And I guess I will not see you on Monday, but I will see you next Wednesday. You guys have a beautiful day.